Welcome. In this session on natural deduction, we'll explore some ways in which a model can satisfy a formula. To do this, let's establish some of our assumptions for this session. What we'll do is we want to model a set of functions and a set of predicates. This will be a model, and we'll vary that model. We'll have to have a set of variables. In this case, we'll only need x, and perhaps we'll get to y, but let's suppose that we just need x. We'll have to have a map that takes a variable to a literal. We'll need to have a way to drive a variable to a concrete element when we explore how the model satisfies a formula. Let's suppose that we have a partial model of the integers, of the whole numbers. And so our functions, all we'll need for this session are I for index and s for successor. We'll just have two predicates. One is q and one is r. And let's suppose that our universe of discourse is the natural numbers. To set this up, we'll say that when we use the nullary function I, that it is assigned to the concrete number 0, which is where the natural numbers begin. And let's suppose that when we need it, our successor function takes a term and it maps it to the term plus 1 in that natural numbers. What we'll do now is we'll invert the thinking that we had previously. What we'll do is we'll start out with a formula. So we'll start out with some formula, and then we'll try to create a model in which that formula is satisfied, and then we'll try to create a model in which that formula is not satisfied. So that's what we'll try to set up. And now let's imagine that we have some formulas. So the first formula we might try to model is q of the index function. And what we do for a model is we'll say we're going to model these predicates extensionally. So that means that q in our model will be, and now we have to specify a subset of the natural numbers. We could specify the whole set, but let's suppose that we pick the even whole numbers. So that's 0, 2, 4, and so on. And we can quickly verify that if we take the nullary function I, that evaluates to 0, and it is 0 in the set Q for this particular model, and the answer is yes. Now, let's imagine a model in which this is not satisfied. Well, one such model of a predicate would be the odd natural numbers. So we could say that this set is composed of 1, 3, 5, and so on. And we'll note that this is an infinite set. That was easy. Now, suppose that the formula we're given is there exists an x such that x is in the set Q. Well, for a model in which that formula is satisfied, we could use the same predicate. So we could say, oh, that predicate set will be 0, 2, 4, and so on. And certainly it's true that there exists an x. Let's be careful now. What we're saying is that for our model, that the model satisfies a formula subject to a mapping of x to a concrete element. And let's recall that we can't assign x to I because I is a function. It can't be a term. It actually has to be a concrete entry of our universe of discourse. So can we do that? And the answer is yes. I can construct a mapping from x to a such that Q of X is satisfied, so I could map it to the value 2, for example, and that formula would then be satisfied. Now, under what model is that formula impossible to satisfy? Well, what we have to do is make sure that whenever we look for X in the set Q, it's never present in the set. So what set has the property that no natural number is in it? And this has to be a subset of the natural numbers. Well, could we use the empty set? And the answer is certainly. We're certainly allowed to use the empty set. Now, suppose that our formula is for all X, Q of X. What would satisfy this? Well, it turns out that there is only one set such that if we look for X in the set Q, that it's always present, and that is when Q is the entire universe of discourse. So now we've seen two of the edge examples of extensional definitions of predicates. We're not only allowed to define a predicate as an empty set, sometimes that's the only way to satisfy a formula, and we're not only allowed to have a predicate be the entire universe, sometimes that's the only way to satisfy a formula. Now, if we turn to what model is this never satisfied, all we have to do is pick a subset of the natural numbers that some number is not present in. So I'll take, for this, I could take the odd numbers, but I could take the numbers that start with 1, 2, 3, and so on. That is, I could take every number except the number 0. And there would be, because there is one counterexample, that formula cannot be satisfied in this model. What about a slightly more complicated model? Suppose that we have, for all X, X is either Q or X is R. And now what we're asking is, in what model is it possible that every time we look into the model, that variable is either in that concrete element when we drive it through the map, that concrete element is either in Q or in R? Well, we could say if Q is the universe of discourse, then that left disjunct has to always be true. Let's instead say, suppose that we set Q to be the even natural numbers, and suppose that we set R in our model to be the odd natural numbers. And within this model, that is certainly satisfied. When it comes to this, what we need is a model in which there is something that is not in Q and something that is not in R. So we're starting to use De Morgan-like thinking here. If I pick a Q, I'll take the odd numbers, is 1, 3, 5, and so on. Now what I need to do is construct an R such that there's at least one thing that isn't in Q and isn't in R. Well, there's an infinite number of ways to do that. I could pick R to be the empty set. I could pick R to be the same as Q. Suppose that I set R within this model to be, I like this idea of making it the numbers greater than 0. So 1, 2, 3, and so on. And within this model, if I attempt to map x to the concrete entry 0 in the natural numbers, I will find that 0 is not in the set Q and 0 is not in the set R, and that formula cannot be satisfied. So I now have formulas in which they're fairly simple, and then ones that are getting more and more complicated. Well, there were certain kinds of formulas that we discovered when we were in as early as propositional logic, and certainly when we were doing predicate logic. We discovered that there were formulas that were always true, and we called those theorems. So let's look at what a theorem might be like in terms of its semantics and the models. So let's suppose that we pick a minor variation off of this. Let's suppose that we pick for all x is Q or x is not Q. And the question would be, let's be sure that we're assigning those. So for this formula, the question is, what model, with using the natural numbers as the universe of discourse, in what model is it true? And the answer is, it's always true. That is, for every model that we come up with, that is, for every set Q that we come up with, this will always evaluate to true. Let's take some of the edge cases that we have in front of us right now. Suppose that Q is the entire universe of discourse. Well, in that case, the left disjunct inside the quantifier will always be satisfied when we drive it to a concrete entry. Suppose that we have Q as the empty set. In that case, x is never in that set Q, therefore the negation is true, and whenever we drive x to a concrete entry in the universe of discourse, not Q of x always evaluates to true. So that's interesting, isn't it? That a theorem is satisfied inside every model that we can possibly come up with. Well, there were some theorems, some formulas rather, that we came up with where it looked like it was just not possible to prove them at all. Let's take let's take an example of, suppose we assert either everything is true, or rather we'll assert everything is true, and let's suppose we assert that something is not Q. So that's our assertion. We're going to assert everything is Q and something is not Q. To satisfy the left conjunct of this, the only set that we can pick in our model is A. And then then we look at the right conjunct. And what this is saying is there must be some concrete element of the universe of discourse that is not in the set Q. And we're not allowed to change the set Q between the left conjunct and the right conjunct. Very important. We can't mix models. Once we pick a model, we have to hold it for the entire formula. And for the entire formula means we have to hold it as we explore each of these quantifiers, and we drive those variables down to concrete elements. So this will be never true. So now what we find is that we have at least three kinds of formulas here. We have contingent formulas. These formulas, all of these first four, are contingent in the sense that there is a model in which those formulas are satisfied and a model in which those formulas are not satisfied. This formula is a theorem, and it appears that that theorem is satisfied in every possible model, and this appears to be sort of a not theorem, the opposite of a theorem, and it's not satisfied in every model. So we will refer to this kind of formula as being unsatisfiable, and that will be a topic for later sessions.